Alright, welcome. In this video, we're going to start a new unit over graphing trig functions. And so in this video, we're going to start small. We're going to start by graphing the parent functions y equals sine x and y equals cosine x. Alright, now in order to graph y equals sine x, on an x-y axis, we're going to need to think back to the unit circle. So I'm going to bring in one of those. And I'm going to try to do this for you like as quickly and without it, getting lost in the numbers as much as possible. Like just really big picture here. So I'm going to be thinking about the extreme values of sine, like really the four main corner points on the unit circle. I don't really have a good name for these. Okay, so 0, pi over 2, pi, 3 pi over 2, and 2 pi is what I'm talking about. So, to go on the unit circle, remember we started the far right edge, and that's theta equals 0 radians. Okay, that's right there. Okay, and we're going to be interested in tracking the y-coordinate of this point as we move around the circle. So I'm going to say it once, and then we'll fill in the table. So right here at theta equals 0, the y-coordinate is 0 because I'm on the x-axis. Then we rotate counterclockwise, and as theta increases to pi over 2 radians, we go up to the top of the circle, and that's the point 0, 1. The y-coordinate is at its maximum of positive 1. Okay, then at theta equals pi radians, that's the far left edge of the circle, I'm back onto the x-axis, my y-coordinate of the point is 0. Then at 3 pi over 2, that's the very bottom of the circle, y-coordinate is negative 1. So, now I'm going to start filling in the table and putting points on the graph. So, first I'm going to say, all right, sine of 0, that's at the far right edge, y-coordinate is 0. So, my point that corresponds to x equals 0 will be on the x-axis. I'm just going to decide it's right there. It doesn't matter really where you put x equals 0 on your graph, but I'm just going to put mine right there. Okay, at pi over 2, the y-coordinate was 1, so sine of pi over 2 equals 1. And I'm going to just decide what I think y equals 1 is. It's up there above the x-axis. This is going to be what's important. This isn't going to be the best graph of y equals sine x ever. I'll show you how to make a better one in a couple minutes here. But for now, this will do. At pi, that's the far left edge of the circle, the y-coordinate is 0. So I'm going to plot that point right there. And then at 3 pi over 2, I'm at the very bottom of the circle, the y-coordinate's negative 1. Okay, so I need to go down by 1. And I'm kind of having some doubts about like the width of my intervals here, but it's okay, right? Part of my message is that we need to not be obsessing over our graph all that much. And then, at 2 pi, that's pretty much the exact same as 0, so I would expect the output to be the same, and I'd be back to where I started. I'm going to have more to say about that here in a few minutes. Okay, now, at this point, I think I'm going to show you what the shape of the graph looks like, and then I'm going to try to justify it using the unit circle here in a second. Okay, so I'm going to draw the first piece in blue because I'm going to be trying to reason with that here in a second, but I'm going to show you that it's curved. The graph here is curved. And so it's not pieces of a semicircle. And that's kind of why I drew it, kind of tall. I don't want you to think it's pieces of a semicircle. It's also not pieces of a parabola either, but, it's got this curvature to it. And so it makes a wave shape. Okay, and the concavity is, basically, the concavity is switching at each time it goes through this middle line here. But we need to learn some terminology about this, and so I'll bring that in here in a second. Okay, but what I was going to say is, okay, for the blue segment, okay, why is it curved this way? Well, let's think about what's happening as theta increases from 0 to pi over 2 on the unit circle. If we think about it, if we were to really think about that point as it moves along the circle, at first, when theta is near 0 and I'm going up the circle, I'm going up a lot and not very far to the left. So that means I'm increasing pretty fast. But then by the time I get close to pi over 2, I'm doing mostly going to the left. I'm not going up very far. And so I would say that the y-coordinate at this point is increasing at a decreasing rate. So the graph of the function y equals sine x on that theta interval, or on the interval 0 to pi over 2, should be increasing and concave down. And then I'd let you think through, you could pause and think about why, decreasing at a decreasing rate, and why these rates of change are going to be the way they are. But I am going to point out that there is going to be a point of inflection each time it passes through this, kind of medium level. I would also say that you could think about, x equals pi over 6 would give you sine as a half. And pi over 6, is less than halfway between 0 and pi over 2, yet the y increase had done half of the amount of increasing that it was going to do over the interval 0 to pi over 2 at pi over 6. So it had done most of its increasing early, so you could see that it would be increasing and concave down. That would be a different approach on the same thing. But what I want to talk about now is what happens after 2 pi. All right, so we're thinking, x has increased. I've gone all the way around the circle counterclockwise one time. And then I end up right back where I started, here at theta equals 2 pi, which is very similar to theta equals 0. But then I just go around the circle again, and the y-coordinate has the exact same behavior, right? So the graph should repeat itself. And I think that's what I said up above, is that these types of functions will be really useful in describing repetitive scenarios. And that's where we're headed with this, is solving contextual problems. So that means up to my ability to kind of replicate the graph I just drew, it's going to repeat itself there. And if I think about what happened before theta equals 0, this is what we did in the previous lesson before the last test. Really, I just went clockwise around the circle, but the same kind of thing happened. And if I think about going backwards, well, the pattern is going to repeat itself. So I'm going to put in some more points, and I'll get what we would call another full cycle of the graph. So the last thing I'm going to do is bring in a y-axis, and I had said that kind of that beginning of the blue arc was x equals 0. And x equals 0 is the y-axis, so I put that right there. Okay, so that's going to be the graph of y equals sine x. It makes a wave that just repeats itself over and over and over again. What I might emphasize is kind of like the most important thing for you to remember about the graph of sine x is what it's doing right there at the beginning, at x equals 0, at least on the standard graph. It is increasing and at the middle. Okay, and we'll have more vocabulary terms here, but that's what I'm going to say about that for now. All right, now having said that, we need to talk about a periodic relationship and the meaning of the word period. So a periodic relationship can be identified between two aspects of a context if pretty much we're demonstrating a repeating pattern. That's the key thing there, and I copied the text just right from the AP Pre-Cal course description. That's one of our essential knowledges, is that a periodic relationship, if they say it's periodic, that means it repeats itself at standard intervals. And that standard interval where it's repeating itself, that's called the period. Okay, so I think the easiest way to see this on these graphs is to kind of go from like the maximum to the next maximum, but you won't always be given that much graph or that much table to see. And so it's really going from any point to the next equivalent point on the graph, kind of like when you've completed one full cycle. So from going to the maximum to another maximum, that would be one full cycle. Okay, but, this isn't really all that labeled, so I might, get rid of those markings and say, okay, well, I know that this is x equals 0, and the full period would be when I go back to being in the middle and coming up. Okay, so that would be, gets the full cycle of the graph. It went up, then down, and then up. I've gotten all of the activity that's going on here. And the time where it went back and repeated itself was back where I got to where I started on the unit circle, which was x equals 2 pi. Okay, so from 0 to 2 pi, we know that's kind of our standard interval for unit circle stuff. That's going to be the standard period for the function sine x, and as we'll also see for cosine x. So the period is equal to 2 pi. So for the graph of cosine, I'm going to do the same thing, and I'm going to go a little faster. So I'm going to think about, my most extreme points, and I'm going to think about a unit circle. And I'm going to say, all right, starting at x equals 0, like theta equals 0, the x-coordinate of that point is going to be positive 1, because I'm as far to the right as I can possibly get on the unit circle. Okay, so I'll just say, all right, I'm going to start there, and the output is going to be 1, because that's going to be the output of cosine is like the y-coordinate on the graph of cosine, which is the x-coordinate on the unit circle, which I know can be a little bit tricky, but think about we're graphing y is cosine of x. And so we're going to see that this is going to be another repetitive graph. Okay, at x equals pi over 2, cosine, the output, the y-coordinate on our new graph is going to be 0. Okay, at x equals pi, cosine of pi is negative 1, cosine of 3 pi over 2 is 0, and cosine of 2 pi is back to where we started, back to 1. Okay, so I can graph maybe one cycle of this, the terminology, and just like before, it's curved. I'm going to try to talk you into why it's curved after the fact, but there we go. Okay, and we could see that, okay, again, I could go back around the circle, so I could have the same thing happening, and I might put, a couple of more points on this graph. Hold on, that's not going to be good enough. I can shoot for at most 2 more of these, I think. And even still, I think I kind of messed that up. Okay, but you know, you get what I'm saying here, and then it's going to go back. I hope that this ends up looking good. I was pretty careful about the points when I was setting them up in the first place, but yeah, it's another repetitive wave graph. Okay, where I've got a y-axis coming through there, because that's where I started. Okay, now, if we're thinking about as x increases from 0, or yeah, x increases from 0 to pi over 2, the x-coordinate here is decreasing. Okay, as I move up the circle. Okay, and at first it's not decreasing by all that much because I'm spending most of my energy going up along the circle. But then eventually, as I get close to pi over 2, I'm going to be going mainly to the left, and so I'm going to be more decreasing. So this is decreasing at a decreasing rate, decreasing and concave down. So this is the graph of y equals cosine x. But what I would point out at this point is that we've got here a maximum at x equals 0. And if I went back to the graph of y equals sine x, we might notice that we have the same overall graph, but with a maximum here, where the output's 1, that's at x equals pi over 2. So what I'm proposing is that maybe the graph of cosine is actually just the same as the graph of sine shifted left by pi over 2 units. And so that's going to give us a trig identity. Cosine of x is equal to sine of x plus pi divided by 2. Our reason will be what I just said, that the graph of y equals cosine x is the image of the graph of y equals sine x after a horizontal translation by negative pi over 2 units, pi over 2 to the left. Okay, and that's going to be a valid formula. That's probably not the version of this trig identity that you would see in most pre-cal textbooks, but that's one we'll just, it's not one you just have to know in a moment's notice, but it's one that makes a lot of sense considering the graphs. All right, so another piece of terminology you need to know is a sinusoidal function. So it sounds like it's just going to be like sine x, right? But a sinusoidal function is any function composed of additive and multiplicative transforms is probably behind my face, of f of x equals sine x. And I'm telling you that the cosine function is a sinusoidal function because of what we just saw, that cosine x equals sine of x plus pi over 2. And if I think about it, that is an additive transform. The additive transforms are the translations, up, down, left, right, and that's what we just saw. Okay, so the cosine functions count as a sinusoidal function, and that's something you need to know for AP Pre-Cal. All right, now the other thing that I want to point out to you about the graph of y equals cosine x is that it's starting at its maximum. I already pointed it out, but oh no, that's not what I wanted. That's what I wanted, was to emphasize that starting point, that it's starting at the top, starting at its maximum, and that'll be important for us when we go, kind of in the next video to graph transformations. Right, now before I end this video, I want to just kind of talk to you about a couple things. First, the window pane graphing technique for sine and cosine. We're going to get started with that. And then also a couple more vocabulary pieces beyond period and a sinusoidal function. So the amplitude of a sinusoidal function is half the difference between its maximum and minimum values. Well, I'm just going to draw you a replica of the graph of sine x really quick, and all we need is a rectangle. So oftentimes in this class, you're going to be given a rectangle that's divided up into like 8 squares, but that's not going to be quite right. What we do for sine, like I was saying earlier, it starts in the middle going up. So I'm going to say, all right, I can just draw this as my general pattern. And I can graph one period of it. And we'll see that when we go to do transforms, this is going to make our life way easier. But for now, I just want to kind of emphasize one thing right now, the amplitude. Okay, and when we graph y equals regular sine x, which did start at the middle coming up, the amplitude, okay, half the distance between its maximum and minimum values. Well, the minimum was -1 and the maximum was 1, and the middle was 0. We'll have a name for that in a minute. But half the difference is, well, that's just the distance from the middle to the top. And we're going to call that the amplitude. So that's an amplitude, and this is also the amplitude. Amplitude of a wave, maybe something you've heard about in a science class or something, but the standard amplitude for the standard sine function, for the standard sine graph, the amplitude is going to be 1. And the same thing would be true for the cosine function, but I'm going to move on and talk about midline. I've kind of been working around that terminology on the whole video, but the midline is determined by the average of the maximum and minimum values for the function. But maybe this time I'll graph y equals cosine x. Now cosine x, like I was saying, it starts at the top, and then it goes down, and then it goes up. So what we could do is kind of just the same window technique, graph one period of cosine like this. Okay, and that'd be great. Okay, but what I really want to emphasize is that cosine starts at the top, which was 1, and then it goes eventually down to the bottom, which is -1, and then it recovers once again. But that midline is what's in the middle. It's the average of the maximum and minimum values. And in the case of y equals cosine x, halfway in the middle would be 0. So I could say that the midline for the graph of y equals cosine x is y equals 0. And I could say the same thing about y equals sine x, right? It should be very similar. You saw it above. Halfway in between -1 and 1 is going to be 0. All right, now the last thing we're going to need to talk about before we move forward and start graphing the transformations, which is going to be a little more involved, is y equals negative sine x and negative cosine x. Because if we have sine, cosine, negative sine, and negative cosine, we can just kind of start with those skeletons and move from there. So let's start with y equals negative sine x. I'm going to draw a new window, right? We got two graphs. I'm going to draw two windows, and we're going to be able to start from there. And if we needed more, we could just like kind of double the windows as long as we needed to. But I'll show you that when the time comes. Okay, for y equals negative sine x, we know that positive sine x starts at the middle and then goes up. Well, negative sine x is going to be a vertical reflection, a reflection across the x-axis. So it's going to go upside down. So rather than going up, the graph will go down. And so it'll be going down and then back to the middle. I'm just going to try to make this as good as possible and estimate halfway. It's easier to estimate half than a quarter. And so I'm going to go, all right, this would be down here, then back up. And this is kind of like the parent graph. Okay, and then for y equals negative cosine x, I'm going to need a new window. And so remember, cosine x starts at the top, starts at its maximum. So negative cosine will start at the minimum. And so that'll be down here, starting at the very minimum. And then it will increase to the maximum and then come back down to the minimum, because it's the exact opposite of the regular cosine. So I'll have one there and one there. That looks pretty good on my guide. And then I just kind of keep that same usual shape going. And oh, that one was pretty bad. Okay, but like I said at the very beginning, as long as the increase, decrease, and the concavity is right, I don't really care. It's not, nobody's going to be saying like, oh, this art isn't quite good enough, we're not going to give you the credit. Okay, because really, as you'll see in the free response problems, like later on in this unit, we don't ever actually have to produce the graph ourselves. We're either working with the graph they give us in the free response section, or we're answering questions about a graph in a multiple choice setting, and neither of those require us to have like super strong art skills. So that's going to be all for this video. In the next one, I will do some transformations of sine x and cosine x. That's all. Thanks for watching.